Okay, so I'll check back at the 15-minute mark to get everyone else because they're dragging their feet today. Okay. All right. So welcome, scholars. Let me see. So no major announcements. We're at the top. We're at the top of week. I think this is week 10, right? So week 12, we can anticipate exam 3 over chapter 2. Okay. I mean, we're actually rapidly approaching the end of like all the new material. I think we might have 2 more sections after chapter 2, maybe 1 or 2, something like that. Yeah, and we're gonna have the Thanksgiving holiday. It's gonna be over. It's gonna be over quickly. So it's a good idea to try to go ahead and get caught up, or you want to try to get as far ahead as possible. Hopefully, you can like finish everything, and then just get your exam submitted. But okay, so today we're going to continue chapter 2 of polynomials and rational functions, and we're going to be working on section 2.2 polynomial functions. Okay. A few objectives here. We like to learn properties of the graphs of polynomial functions, determine the end behavior of polynomial functions, find the zeros of a polynomial function by factoring, identify the relationship between degrees, real zeros, and turning points, and graph polynomial functions, okay? So we have this definition that a polynomial function of degree n is a function of this form, where n is a non-negative integer and the coefficients, this a sub n minus 1, all the way down to a naught, are real numbers where a sub n is not equal to 0, right? So a polynomial function, another way of articulating it, hey, come here. Malachi, come here. Come on. Come here. Come here. Sorry about that. So a polynomial is just a finite sum of monomials. Where a monomial, all it is, you have some real coefficient times some variable x and some non-negative integer exponent, right? Once you can identify something as a monomial, then polynomials are easy to identify, where it's just going to be a finite sum of monomials. These are all monomials. Okay, again, n is a non-negative integer. The coefficients, these are real numbers, where the leading coefficient is not 0, okay? So that's a mouthful, but I feel like once you start working with some of these, you'll be able to identify them easily. So the term an x to the n is called the leading term. The number an is called the leading coefficient, and a naught is our constant term. A constant function f of x equal to a, where a is not 0, which may be written as f of x equals a times x to the power 0, is a polynomial of degree 0. So the degree of a polynomial is the highest power on any variable. When you have a constant polynomial, in other words, a function equal to just a real number, not equal to 0, then that's called a polynomial of degree 0, okay? But the 0 function, f of x equal to 0, has no degree, right? Because you can write it an infinite number of ways. F of x equals 0 is the same as 0 times x squared, which is the same as 0 times x to the 7. You can write that other term an infinite number of ways. So because of that, we say that this function has no degree when you have f of x equal to 0. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials, respectively. Okay. So cubic is a degree 3, quartic is a degree 4, quintic is a degree 5. Let me see the time. I'm gonna give them another 10 minutes and I'll check it at the 15-minute mark. Okay. So then we have this expression. So given a polynomial expression, right? Again, this is a polynomial. Then the function f defined by this, we call this a polynomial function. And when you have a polynomial equal to 0, we say that's a polynomial equation, all right? So a few different ways that we can express a polynomial. So once you identify a function as polynomial, then the domain of a polynomial function is going to be the set of all real numbers, right? So the domain of a polynomial is all reals. Some properties, other properties of polynomials. The graph of a polynomial function is a continuous curve. So here on the left, you can start at any point and you can get to any other point by tracing the graph without having to pick up your pencil, right? So that's what we mean by a continuous curve. Versus on the graph on the right, say I start at this point, right? And say I want to get to when X is somewhere on the right-hand side. I had to pick my pen up in order to jump that gap, right? So because the one on the right has a hole or a gap or a break, then it cannot be the graph of a polynomial function because it's not continuous. Okay. Another property for polynomial functions is that the graph of a polynomial function is a smooth curve. So there are no sharp corners or edges or anything like that, right? So the graph of a polynomial has two features. The graph is a smooth, continuous curve. So smooth meaning there are no sharp corners, and continuous meaning there are no holes or gaps or breaks. So state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. So for instance, if we're looking at the first one, if you had to guess, would you guess that part A is a polynomial, yay or nay? If you had to guess, would you say that this is a polynomial, yes or no? Right. So I think we said polynomials were a finite sum of monomials, right? Monomial, you have a real coefficient to some non-negative integer exponent. So we have one monomial plus a second one plus a third one, all right? So we have a finite sum of monomials, so then this is a polynomial. So if you look at part B and you're asking yourself, is that a polynomial? All right, what do you think, yay or nay? So B is not going to be a polynomial because the domain is not all reals, right? So we just said that a moment ago, the domain of polynomials is all reals. This domain is restricted to all the numbers between 1 and 5 inclusive. So because the domain is not all reals, then this cannot be a polynomial function. Okay. And this is kind of reiterating what we just discussed. Let me see the time. I'm gonna give them another a little over 6 minutes. So a function of this form is called a power function of degree n, where a is a non-zero real number and n is a positive integer, right? So the power function is basically going to be f of x equal to a monomial. Okay. So then if you consider the power function, if n is even, right, then if we think about negative x to an even power, right, if we have an even number of negatives multiplied, then it's gonna finish positive. So then what that means, what's going on is if we're doing f of negative x and we're finishing with f of x, that's the definition of a function being even. Let's say that one more time. When we consider f of negative x and we finish with f of x, that's the definition of a function being even, right? So then once we identify a function as even, that means that the graph is going to be symmetric to the y-axis, okay? And the graph is going to be similar to the graph of y equals x squared. So if you think about y equals x squared as a U-shaped curve, notice that the tail end, they go off in the same direction, though, as x goes to either positive or negative infinity, the y's go in the same direction. They either both go up or they both go down in this case, all right? But they go in the same direction. I'll give them a little over 5 minutes, then I'll check for anybody that missed the first wave. So we saw where we looked at a power function of even degree. Now we want to look at a power function of odd degree. So given this power function, now say the n is odd. So then if we consider negative x to the power of n, an odd number of negatives is ultimately going to be negative, so you can express it this way. So then what's going on is if we're doing f of negative x, we can finish with negative times f of x. That's the definition of a function being odd. Okay. That's the definition of a function being odd. And a function being odd means that it's symmetrical with respect to the origin. Origin symmetry just means, whenever you have x comma y, you also have negative x comma negative y. All the points are symmetric and equidistant around the origin, right? So it's almost like the S shape, right? It's the best way I can visualize it is like, like if you put your thumb on the origin and you cut it in half along the x-axis, if you rotate the top half by 180 degrees, it'll match the bottom half. Yeah, so, so we talked about a function being even. Now with the function being odd and the origin symmetry, the tail ends typically go off in opposite directions, right? They go off in opposite directions. Okay. So we have these 4 cases. This is missing something where you're gonna have to wait. You gotta bark like a maniac. So now you're gonna be in timeout until I'm done. Oh, you stink. You need like a bath or something, or a toothbrush. I think it's more so a toothbrush than anything. So we want to consider when n is even. All right, the degree of the polynomial is even. All right. So, okay, the leading coefficient is positive. That means the right-hand side goes up. If the degree of this power function is even, that means the other side does the exact same thing. Okay. The way I remember is that even means the exact same. Odd means opposite. Okay, so in this example, we looked at when the leading coefficient was positive. In the next example, we're going to look at where the leading coefficient is negative. All right. And we're still working with, let's just copy and paste. We're still working with n is even here. Okay, so let's see the time. With the leading coefficient being negative, what that means is that our polynomial is going to go down to the right. Because n is even, that means the other side does the exact same. It's going to go down as well. Okay. So we saw 2 cases where n was even. Now we want to consider 2 cases where n is odd, right? So just like before, if the leading coefficient is positive, and in this case, our n is odd, okay. So the leading coefficient being positive, that means our graph goes up to the right. Because the degree of our power function is odd, that means the other side is going to do the opposite. So if we go up to the right, that means the other side is going to go down to the left. Okay. And then the final case is where the leading coefficient is positive. Sorry, leading coefficient is negative, and we're still working where n is odd. So then a negative leading coefficient means we're going to go down to the right. And if n is odd, that means the other side is the opposite. So we're going to go up to the left. Okay. All right. Let me go ahead and check attendance before I do this one. All right. This one. Okay. This one. This one. Okay. All right. And let's keep the party going. All right. So if you're just joining us, we are working on, is this the right thing for you guys? Yeah, this is fun. Polynomial functions, right? And so we just kind of discussed power function or in-graph behavior of a power function. So, I think the recording is available. You have to just use that. But let's take a look at this. So given this polynomial function, right, of degree 3, again, the degree is the highest exponent on the variable, so you see it there. We want to show that this polynomial is approximately equal to 2x cubed when the absolute value of x is very large, right? So let's just start with, this is kind of like a demo. You wouldn't really think this way, but we need to talk about it. So let's start with the given polynomial, and we're given that 2x cubed plus 5x squared minus 7x plus 11. So now given this polynomial, let's factor out x cubed from all the terms. So if we factor out x cubed, from that first term, we're going to be left with 2. The second term, we're going to be left with 5 over x. The third term, we're going to be left with the negative 7 over x squared. And the last term, we're going to be left with 11 over x cubed. Okay? So we factor out x cubed from each term. So then now, let's see. So let the absolute value of x get very large or go to infinity. Then the following thing happens, right? As x gets closer and closer to infinity, these terms get closer and closer to, here, let's copy and paste. So as x goes up to infinity, this term tends to 0, this term gets closer and closer to 0, and this term gets closer and closer to 0. So they all tend to 0. So then that's going to be approximately equal to 2x cubed, right? So we showed that the original polynomial is approximately equal to 2x cubed when the absolute value of x is very large. We'll just put a box, okay? Right. So what this is telling us is that given a polynomial, as x goes off to positive infinity or negative infinity, it's going to behave like this power function that we just discussed. So we just went through four scenarios with this power function and the in-graph behavior. So then we can extend those scenarios to more generic polynomials. Okay. And so here's a type version of what we just did. Okay. So you can see where they factored out x cubed. And then when the absolute value of x is very large, these 3 terms get fairly close to 0. So they essentially go to 0. So therefore, the original polynomial is approximately x cubed times this, which is approximately 2x cubed, right? So the leading term test is an extension of those 4 cases that we talked about a moment ago. So given a polynomial function where the leading coefficient is not 0, then the leading term a sub n x to the n, and the leading term is a sub n x to the n, then the behavior of the graph of f as x goes to positive infinity or negative infinity is similar to one of the 4 graphs and is described as shown in each case. The middle portion of each graph is indicated by dashed lines. It is not determined by this test, right? So this test doesn't tell us anything about the middle, but it does give us some insight into the long-term behavior, right? And so case 1, where the leading coefficient is positive and n is even. N is even. Let's copy, okay? So just like before, the leading coefficient is positive, means our graph goes up to the right. Because n is even, the degree of the polynomial is even, then the other side does the exact same thing. It goes up to the left, okay? So when we're doing this leading term test, the way I remember is that even means the exact same, odd means opposite. Okay, here n is still even. And now our leading coefficient is negative. So with a negative leading coefficient, that means our graph goes down to the right. Because the degree of the polynomial is even, that means the other side is the exact same, so we go down to the left as well. Okay. Again, this test doesn't tell us anything about the middle, but it tells us about the long-term behavior of these polynomials. Okay. So we did, now we want to consider when n is odd. Okay. So a positive leading coefficient means we go up to the right. If the degree of the polynomial is odd, that means the other side does the opposite, so we're going to go down to the left. Okay. And then the final one, the leading coefficient is negative, but n is still odd. So a negative leading coefficient means we go down to the right, and then because the degree of the polynomial is odd, that means the other side does the opposite. So we're going to go up to the left, right? So those were the 4 cases with the leading term test. 2 of them for even, 2 of them for odd. A positive leading coefficient means we go up to the right. Even means the other side does the exact same. A negative leading coefficient means we go down to the right. Odd degree polynomial means the other side does the opposite. Okay, so that's a summary of those 4 scenarios. Okay, you got to wait. You want to draw all this attention, so now you get all the attention. You have to wait. Ugh, but I don't know who's being tortured worse. Who's being tortured worse, you or me? You have to be still, but I gotta bear the smell of your breath. I think it's your breath. Some smells. You need a bath or a toothbrush. Use a leading term test to determine the end behavior of this graph, right? So, 2 pieces of information that we need. The leading term, so let me see, our a sub n, which is going to be -2 in this case. Notice that this is negative, it's less than 0. So what that means is that our graph is going to go down to the right. Okay. And then the degree of our polynomial in this case is the highest exponent, which is going to be 3, which is what? Odd. So that means the other side does the opposite, so it should go up to the left, right? Again, this doesn't tell us anything about the middle, right? It doesn't tell us anything about the middle, but we know that in the long term, it should go down to the right and up to the left. Okay, and we can see it here. Oh, and these are typos. Let me do what I did before. Stop. And something like here. Let's copy, paste the image. Let's crop. Let's copy. Okay. Delete this one. Let's paste. So those little R's, those are typos. It just didn't transfer properly from one platform to another. So those are they just didn't compile properly. Those are supposed to be arrows. Okay. So using the leading term test, let me check you guys on Zoom real quick. Nope. You gotta wait. Right here. All right. So this is just a type version of what we just did, right? So we had this polynomial. The degree of the polynomial is 3, which is odd. The leading coefficient is -2. Again, it's just negative. So it's case 4. So we said it's going to fall to the right and rise to the left. You can see it falls to the right and rises to the left. Okay, let's keep going. So then I know it's a lot of like terms. I mean, that's just the nature of this. We'll get some practice with some examples. I don't know about this class, maybe 1 or 2. If f is a polynomial function and c is a real number, then the following statements are equivalent. C is a 0 of f is equivalent to C is a solution or root of the equation f of x equals 0, which is equivalent to C is an x-intercept of the graph of f, right? So then these are 3 ways of saying the same thing, right? So whenever we find the x-intercept, that's the same as find the solution or root of the equation f of x equal to 0. And that's the same as if we say, find the 0 of this function, right? So these are all saying the same thing. So then here we're asked to find the zeros of each polynomial function. So let me see. So for part A, I might have enough space here. We have f of x equals x to the 4 minus 2x cubed minus 3x squared, right? If we're asked to find the zeros, we want to go ahead and set this equal to 0 and solve. So we have these 3 terms. If we want to solve this, it's a good idea to factor any greatest common factor. In this case, the GCF is going to be x squared. Okay. If we factor out an x squared from each term, we're going to be left with x squared minus 2x minus 3 equals 0. Then we want to factor this further. Because the second one is a negative, I know my signs are opposite. So I know I have a plus and a minus. Looking for 2 numbers and multiply to give me -3 and add to give me -2. So it's going to be -3 and 1. Okay. So from here, we can use a 0 factor property. When you have 2 or more things that multiply to give you 0, you basically set each thing to 0 and solve. If we do that, we'll get x equals 0, or x equals -1, or x equals 3. Okay. Okay. Let's work on part B over here. Stop. No, you gotta wait. Like, you just have to wait. Otherwise, you act like a maniac. Okay, part B, we have this g of x, x cubed minus 2x squared plus x minus 2. Okay. Can we do factor by grouping? Will that help us? Okay. I'm going to try a factor by grouping, where I'm going to group the first 2 together. Okay. So if I consider the first 2 and factor out the greatest common factor, it looks like we can factor out an x squared from both of those. And it looks like we're going to be left with, looks like it's x minus 2. Notice I think we have another x minus 2 over here that's persisting. Okay. So then we have a left hand plus the right hand side. So then they both have a common binomial factor. We can factor out the x minus 2. And we're going to be left with x squared plus 1. Okay. If this were x squared minus 1, then we could factor that further. That would be the difference of two squares, but there is no sum of two squares property. So that just kind of persists as is. So if we set each of these to 0 and solve, this first one, if you think about it, let me see. This is basically a parabola that's been moved up by 1. So if we're trying to see where it's going to be equal to 0, and again, we should have had this equal to 0 over here. This guy over here won't ever be equal to 0. There's no value of x that can make that 0, not a real number. So then it's just a matter of this blue part being set to 0 and solve. If we set that to 0 and solve, we get x equals 2. Now we should check this. We should check this, but I don't think I am right now. Okay. So we got 0, -1, or 3. And then we got 2 was the only result we got for part B. So you see the 0, -1, and 3. And then we get x equals 2, right? The only 0 of G is going to be 2, since this other one is always greater than 0 for all real numbers x. Because again, if you think about the graph, this is a U-shaped curve that's been moved up by 1. So it's never going to touch the x-axis, so it'll never be 0. Okay, for this one. For this one, x equals 2. Okay. Let me check Zoom again. Do that. Then we have the intermediate value theorem. Let A and B be two numbers such that A is strictly less than B. If f is a polynomial function such that f of A and f of B have opposite signs, then there's at least one number C between A and B for which f of C equals 0, right? So here's a pictorial representation of that. So notice here our f of A is positive, right? We have a positive y value. Over here, our f of B is negative. We have some C between our A and B. So A is here, B is here, C is here. So then, because the property of polynomials is that the graph is a continuous unbroken curve, and if the sign, notice the sign changed, it went from positive to negative, then there has to be some C between A and B such that f of C equals 0. Basically, it has to cross the x-axis is what it's saying. Over here, it's the same thing, right? Our y value is negative, or y value is positive. So there has to be some C between A and B such that f of C equals 0. In other words, it has to cross the x-axis somewhere between. So that's the property of polynomial functions because their graphs are continuous unbroken curves. Okay. Let's try to go for like at least 5 more minutes. Let's see. So the intermediate value theorem, and you could have more than one. It can cross the graph more than once, right? So this is kind of a repeat of what we had before. It's just saying that you could have multiple zeros between those endpoints, A and B. Okay. I think I'm gonna just go ahead and make this the last one. I'm a little bit spent today. So show that this function has a real 0 between 1 and 2. And basically all we do, so we want to show that it has a real 0 between x equals 1 and x equals 2. So we can plug in, we can find f of 1, get a result. We can find f of 2, get a result. And as long as they have opposite signs, then that's enough to show that it has a real zero between 1 and 2, right? So for instance, if we say f of 1, that's going to be -2 times 1 cubed plus 4 times 1 plus 5. That's going to be -2 plus 4 plus 5, which is 7. So notice that that one is positive. And then if we consider f of 2, -2 times 2 cubed plus 4 times 2 plus 5, 16. So -16 plus 8 plus 5. And I think that one's -11, is that right? 8 and 5 is what? 13. So -3. And notice that this one is negative. It's -8, yeah, -3, right? So, and we can identify this function as a polynomial, right? Finite sum of monomials with real coefficients and non-negative integer exponents. So f of 1 was positive, f of 2 was negative. So then there has to be a 0 between 1 and 2 by the intermediate value theorem. Let's see what the type notes say. So we got 7, we got -3. So f of 1 and f of 2 have opposite signs. So by the intermediate value theorem, f of x has a real 0 between 1 and 2. Okay. All right. I think that's going to be enough for right now. Okay. Are there any questions before we go our separate ways? Okay. So next time we will work on some of the homework associated with this. And let me go ahead and make a copy of this available. So I'm going to send it to Box. Fall College Algebra 1 into the note section. If there aren't any burning questions, going once, going twice. So when this bar finishes loading, we're going to go ahead and call it a day. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Okay, take care. Peace.
Thank you.
Yeah.